All right, so today will be the last lecture that we have on fundamentals and general topics, and we'll start into applications. The first application we'll talk about is controlled drug delivery. And before we start doing that, I'll finish up with some more fundamental information that's going to be useful for the homework, but also for the discussion of controlled drug delivery. And I'll start it by discussing it in the context of experimental measurements to determine solubility and diffusion coefficients. So if the transport of small molecules through polymers is governed by solubility and diffusion, then it's important to have mechanisms available to measure those parameters. And I'll talk about one today that in various manifestations is a key way to carry out those measurements. It's called a kinetic sorption or a kinetic desorption study. And so the way this works in general is one will take a sample, like a membrane, for example, and soak it in a solution or in an environment that contains a solute of interest. In this particular case, we're talking about a membrane that might swell some in water and then absorb ions out of solution. So this might be a reverse osmosis membrane or some other type of desalination membrane, or perhaps a membrane that's absorbing a solute like a drug from solution to later release it. And so after some time of the sample sitting in a solution that contains the solute of interest, for example, sodium chloride, the sample will come to thermodynamic equilibrium, and it will have absorbed all of the water and all of the salt that it can. If you take it out of that solution and then put it into pure water and stir it so that the solution stays well mixed, over time, some of the salt that was in the sample will come out. And as it comes out into the water, you can detect that in terms of a rise in electrical conductivity of the water. And from that conductivity rise with time, diffusion coefficients can be determined. I'll show you what this means in a moment. And from the total amount of salt that's extracted from this sample, that was the amount that was dissolved in the sample when it was equilibrated with a solution at this concentration. And so you can determine the partition coefficient by measuring the total amount of salt released and knowing the amount of salt in the external solution. So you can determine in this single experiment both the partition or solubility coefficient as well as the diffusion coefficient, and then be able to predict the permeability coefficient, because it's just the product of those two. Another example from the gas phase transport studies is a McBain spring quartz balance system, and this is a very old device that works on a really simple principle. You take a polymer sample and hang it on the end of a quartz spring, and these springs are very delicate and fragile. They tend to be about this tall, and they will extend 100 millimeters for every milligram of load. And so they have a very Hookean response, so the load on them is very directly related to the spring extension. And so you hang a sample off the end of one of these springs that extends partly, and then through a gas manifold system, you introduce gas into this chamber that would have a penetrant of interest. I'll show you some data in a moment for propane sorption in a polymer. And as the polymer picks up the gas, what happens to its weight? It goes up. And what happens to the spring? It extends, and then you measure the spring extension. In the days before electricity, we would do that with a real eye there. Nowadays, it's more common to use a camera and automate this. When I started in this business 30 years ago, I could tell whether or not the students were in the lab working by looking at their kinetic sorption data, and if there were gaps in it, then I knew they hadn't been there to actually make the measurements. Thankfully now I have no idea if they're in the lab or not, because all this is accumulated automatically. This sort of system, as you might imagine, was automated. You can buy electronic balances that essentially do the same thing as the spring system, and more recently there are even more sophisticated devices like this Rubotherm magnetic suspension balance, which again is an automated way of carrying out that same simple experiment of measuring the weight of a sample when it is in an environment that contains a penetrant that it can absorb, or when it's loaded with penetrant and then put into an environment like vacuum where that penetrant comes out. You can track weight gain or weight loss either way. So this shows an example of experimental data from such a system, and this is propane gas phase uptake into a polymer PTMSP that has the capacity to absorb a lot of propane. It's a sponge for propane in a certain extent. And so this experiment is started by hanging a sample of this polymer from that quartz spring, initially putting the sample under vacuum so there's to desorb any volatile species out of the material, and then at time t equals 0, exposing it to a fixed partial pressure of propane. And once exposed to this much propane in the gas phase, the polymer mass starts to increase as that some of that propane is absorbed by the sample. Often we'll plot the data as the fractional mass uptake. So this is the mass uptake at time t since the experiment started, divided by the mass uptake at long times after the experiment is over. And so the way this experiment goes is that it will mass will increase initially as the sample is absorbing propane. Eventually though, there is an equilibrium partitioning of propane between that sample and the surrounding environment that's held at this pressure, and so the mass levels off and ceases to change with time. And so the fractional mass uptake then goes from 0 up to 1 over some time scale. And you'll note that we're plotting these data not as mass versus time, but as the fractional mass uptake versus the square root of time. And the initial part of this curve is linear. Part of the sorption isotherm is linear. And I'll come back to that in just a moment when we look at the mathematical analysis of this program, of this particular data. This sort of behavior is not restricted to the gas phase. This is an example of salt desorption from a polymer into water. So this is the analog experiment that I showed you a moment ago, where a membrane has been equilibrated with salt and water and then put into deionized water. The salt that had absorbed into the polymer comes out into that water, and you can measure then the amount of salt released. In these desorption experiments, MT and M infinity take on slightly different meanings. MT is the amount of penetrant released at time t, and M infinity is the total amount of penetrant release, which would correspond to the amount of penetrant that was dissolved in the polymer when it was equilibrated with the initial solution. But you can see that the results, whether they be gas or liquid, sorption or desorption, look qualitatively the same, and we're plotting them in the same way. Fractional mass change versus square root of time, or in this case, square root of time divided by the sample thickness. And that's not an accident. That comes directly out of predictions of the basic predictions of Fick's law. Now, the way that we analyze this is starting from Fick's law, and this is an expression for the flux of penetrant into sample, depends on the diffusion coefficient and the concentration gradient. We couple that in these transient cases with a transient mass balance that says that the time rate of change of the concentration of penetrant at any point is minus the divergence of the flux, exactly like you would apply in a typical mass transfer problem. And then putting Fick's law in for the flux, you can write the generalized expression for that would govern mass transfer in the system. Now, historically, the way the data that I showed you in those plots are organized is under the assumption that the diffusion coefficient is constant, and that turns out not to be a limiting assumption. I'll show you a bit later how we account for the case when diffusion coefficients are not constant in these experiments. But the experimental data are typically analyzed as if the diffusion coefficient were constant, and so it comes outside the derivatives. And furthermore, the experiments are typically set up so that not all of these terms matter. And so one would typically set up this experiment in the form of thin sheets. And so if the x direction is into the edge of this sample, the face over which mass enters the sample primarily for transporting the x directions are the large faces. And if the y and z directions are large, they also have very little surface area for mass transfer to occur. And so the mass transfer occurs across primarily the surface that is perpendicular to the thin dimension of the sample. That's just the way the geometry works. And in that limit, the only term that's important when the thickness is much less than either of the other dimensions, the only term that's important is this first one. It's the one that is in the direction of the thin direction of the sample. And in fact, it turns out that you don't have to have these dimensions be too much greater than the thickness for this approximation to be valid. It turns out that the rate at which mass will enter these materials goes as the square of the distance. And so as you make, for example, the thickness 1/10 that of either of the other dimensions, then it means that the rate at which mass enters from the edges of the sample will be at least 100 times slower than through the primary dimension. And so the way these experiments are typically analyzed is using this form of Fick's law. This is often called Fick's second law, and this I showed you earlier is the Bible in this for analytical solutions in this space, the Mathematics of Diffusion, written by a fellow aptly named John Crank. And if you look at some of the sections of this, you'll see why that's appropriate. And it goes hand in hand with another classic book in this area by Carcel and Jaeger, The Conduction of Heat in Solids. And Crank says that in his solutions, his analytical solutions for diffusion problems, he doesn't give all the possible solutions to diffusion problems because a whole bunch of them are also reported in Carcel and Jaeger's book. If you make the substitution that replace temperature with concentration, replace thermal diffusivity with mass diffusivity, that you get, you can take a lot of the solutions out of the conduction of heat in solids and apply them directly to diffusion problems. And so this would give you the notion, which is correct, that Carcel and Jaeger was published before the Mathematics of Diffusion. And so Crank didn't see the need to rework all of Carcel and Jaeger's solutions if they were directly applicable to mass transfer problems. And you'll recall that that Fick, in his original studies in this area, postulated the law of mass transfer based on analogy with Fourier's law of heat conduction. And so it shouldn't be a surprise then that when you come to analyze problems later, that there's a very close connection between solutions to heat transfer problems and solutions to corresponding mass transfer problems. This is the table of contents from Crank's book, and it's organized, a key part of it is organized around geometry, so diffusion in plane sheets, cylinder spheres, talks about concentration-dependent diffusion, numerical methods to solve diffusion coefficients, and so forth. And so if you work in this field, this is a good one to have on your shelf because it has a lot of useful information and useful solutions to typical problems. So coming back to the absorption experiment, the governing differential equation is shown here. It's a partial differential equation. We need two boundary conditions in x and one in time in order to solve it. And so initially we would typically start with a sample that had a uniform concentration of penetrant, C0, although That's not the case. That doesn't have to be the case. And in fact, you go to Crank's book and it shows you how to solve these problems for cases of arbitrary initial profile of penetrant throughout a polymer. Often, the penetrant concentration is zero in a polymer. That was the case, for example, in that propane uptake experiment. The sample had been equilibrated under vacuum to remove any penetrant from it. So you start in that case with a penetrant-free polymer, but you don't have to do that. And at time equals zero, the concentration, pressure, activity, any way you want to express it, of the penetrant surrounding the sample is increased in a stepwise fashion, or as close as you can do that experimentally, to a point where the new equilibrium concentration in the polymer is C1. And so for all times less than 0, C is equal to C0, and at T greater than or equal to 0 at the boundaries of the film, that is at X equals 0 and L, C is equal to C1. And this, with this initial condition and these boundary conditions, this linear partial differential equation can be solved analytically. And there are two solutions that are of interest. The top one we obtain by the separation of variables method, and the bottom one comes most easily through Laplace transforms. These solutions are give identical predictions of concentration profiles, and I show both of them because they give insightful limits in different parts of the mass uptake spectrum. Now, one of the things that you become aware of as you are doing research and making measurements in the laboratory and then comparing that to experimental models is that there are things that you can calculate, and then there are things that you can measure. And often these are not exactly the same thing, and you have to connect them. Yes, sir?
The second solution seems to give two terms that are exactly the same. Am I? Yeah, but like the first summation.
Yeah, if that's the case, this is then I will go back and check it. That's not quite right. They're not exactly the same. They're close.
Okay.
They shouldn't be identical.
Okay.
I need to go back and read Crank more closely. Thank you for that. Well, what we can model in this system, the fundamental models are postulated based on the concentration of penetrant at a local point inside the film. Now, when I showed you the experimental equipment earlier, it's not measuring that, right? What's it measuring? It's measuring the total mass of material either released from the film or taken up by the film. And so we need a way to relate the local concentration, which can be modeled using Fick's law, to the total amount of mass that is in the film at any given time. And the way we do that is essentially by integrating the concentration profile across the film thickness. This shows the structure of the solution of those equations. And so what's plotted here is the dimensionless concentration as a function of distance away from the center line of the film to the edge of the film. And what I'm showing you is half of the film. So this would be from the center line of the film out to one edge. These profiles would have a mirror image on the other side extending from the middle out to the other edge of the film. So you imagine this being folded out and these concentration profiles being symmetric. Each of these curves is labeled with a number, and that number corresponds to values of dt over L squared, diffusion coefficient times time divided by L squared. And so as these numbers change for constant d and sample thickness, this is just indicating the march of time as this experiment proceeds. And if you look back at the solution, you can see dt over L squared appearing in the time-dependent terms. If you divide top and bottom of this expression by L, you'll have the square root of dt over L squared here. So that's the natural grouping of variables that makes time dimensionless in diffusion problems. So B would have units for example, square centimeters per second. L would have units of centimeters, time in seconds, and so dt over L squared would be dimensionless time. And that falls naturally out of the solution to Fick's law in this case. There are a couple of particular values of dt over L squared that I want to point out to you. One is when dt over L squared gets to be about equal to 1, you'll see that the concentration profile has almost gone as far as it can. At equilibrium, the concentration profile, dimensionless concentration profile, will be stuck here at 1 all across the film. But by the time dt over L squared gets to a value of 1, the vast majority of the penetrant uptake, or in the case of the desorption experiment, the penetrant release has already occurred. And so this is a rule of thumb that you can carry with you for diffusion experiments, is that the characteristic time scale for diffusion to finish is L squared over D, which is dt over L squared equals 1. And I can't tell you how many times that particular rule of thumb has been useful to estimate how rapidly processes will occur and whether or not diffusion is important relative to other mass transfer phenomena in a given system. So that one I would commit to memory. dt over L squared is 1 is the characteristic time for diffusion to be over. Another one that we'll see of interest in a moment is dt over L squared equal to 0.05. And so there's a curve here at 0.04 and 0.06. You can imagine there'll be one in between at 0.05. And that turns out to be, when dt over L squared is 0.05, or about 1 over 20, that turns out to be the point where the sample has absorbed about half of all the mass that it's going to uptake during the entire experiment. And that's often called the half time in a diffusion experiment. dt over L squared equals 1 over 20, or 0.05. So we calculate the mass uptake at any time t, as shown here, integrating the concentration profile across the sample, multiplying by the area. And this mt is the amount of mass that is taken up since this experiment started, and does not count any mass of penetrant that was sitting in the polymer when the experiment started. And so we subtract off any material, any penetrant that had already sorbed into the material before this experiment started. And that's this initial concentration, C0, times the volume of the film, its cross-sectional area times L. And so you can carry out the integration, and you get, again, two equivalent forms of the fractional mass uptake. And I show them both again because they are useful in demonstrating various features of the behavior of the solution of the diffusion. First, just a reminder for these experiments or expressions, particularly those solved by Laplace transforms, often involve error functions. A reminder of what that is. There's a good section on this in Karslaw and Jaeger, and a section of error functions that are important in diffusion problems in Crank and Park, and I think I've put that appendix up for you. Complementary error functions, just one minus the error function. Nowadays, these are built into most of the spreadsheeting programs, so you don't need to go the overland route of actually calculating these guys with series approximations. This is what the error function looks like. The complementary error function would be just one minus that. Another form that often appears in these expressions is the integrated error function. The one that we're most concerned about is this first one, which is related to the complementary error function as shown here. So we have these two equivalent expressions for the fractional mass uptake. This left-hand expression is very useful at short times, times near the beginning of the experiment, because it turns out that all of the terms in this infinite series go to 0 at short enough time. And so as time gets very short, this term gets very large, And as the argument of this term gets large, this term of course goes to 0, and the complementary error function as x gets large goes to 1 minus 1, essentially. It goes to 0. So this whole term goes to 0 for large values of its argument. So at short times, everything here drops out, and the fractional mass uptake is, guess what? Linear in the square root of time. Or, if you wish, linear in t to the 1/2 divided by L. And so that's why we plot the data that way. That's why you see the data be linear initially with fractional mass uptake. And if you have these kind of experimental data, you can determine the diffusion coefficient from the slope of that initial piece of the data. And that's shown here for the salt desorption experiment. The region where the fractional mass uptake is linear in square root time can be used to determine the diffusion coefficient by just taking the slope of that line and knowing the thickness. One put the slope in here, thickness in here, calculate diffusion coefficients. An alternative way to do that is to plug a value of 0.5 into the left-hand side of this equation and calculate the time at which the fractional mass uptake is equal to 0.5, and the diffusion coefficient then is 1/20th L squared over that half time. And that was the case I was showing you in the concentration profile a moment ago. And so you come to MT over M infinity of a half, look down, get the time, and from that t to the 1/2 you calculate diffusion coefficient. So that's how diffusion coefficients are extracted from these experiments. Now initially, the fractional mass uptake is always linear with the square root of time, but it has to eventually bend over and approach 1 as the sample comes to equilibrium. The reason it's linear initially, you can see if you look back at the concentration profile briefly, get back here. So initially, if you imagine again that there's a mirror image of this concentration profile on the other side where the penetrant is diffusing in from both sides of the sample, at very short times, the concentration of penetrant at the center of the sample is 0. And as a result, to penetrant diffusing from this side, this looks like it is diffusing into a semi-infinite medium, right? There's no penetrant, there's nothing here to stop it from diffusing. It's as if it were diffusing into an infinitely long space. And the same thing is happening on the other side. And the solution to the problem of diffusion into a semi-infinite rod or sheet is that the mass uptake then forever goes as linear with the square root of time. Now, as the concentration profiles from the two sides meet, and you start to have a concentration at the center of this film, then the net driving force for transport, that is the difference between the concentration here and the concentration at the lowest value in the film, that net driving force starts to decrease. It goes from a maximum value at the beginning of the experiment and then gradually decreases. And as the driving force decreases, then the flux, remember Fick's law is underpinning this, the flux decreases as the driving force decreases. And so then the fractional mass uptake slows down. So as those concentration profiles meet in the middle, the fractional mass uptake starts to deviate from linear with the square root of time and eventually bends over as the sample fills up, or in the case of desorption, as it exhausts itself. From the exponential solution, we get valuable long time behavior. So near the end of this process, when MT over M infinity is greater than 0.7, that is in the region where the data start to bend over, you get another type of limiting behavior. At long times, only the first term in this infinite series means anything. You can see that that these terms drop off if you have significant values of dt over L squared, these exponential terms drop off very fast with n. So the first term, n equals 0, will have a value of minus pi squared dt over L squared. N equals 1 is already up to 9 pi squared dt over L squared, which, once dt over L squared gets any size at all, the difference between e to the minus that and e to the minus 9 that is enormous, and everything beyond that is in the noise. And so beyond about nt over n infinity at 0.7, it's only this first term that makes a contribution to the fractional mass uptake, and we can rearrange the expression as shown here. And if we plot the log of 1 minus nt over n infinity versus time, then the diffusion coefficient is just the slope of that line. And this is showing data plotted in that fashion to extract diffusion coefficients. Reason you might do this, one, that there's a couple reasons to do it. One is if you have this fractional mass uptake data, you have from it at least 4 ways to estimate diffusion coefficients. One is you can fit all of the data to one of those infinite series solutions. That's the whole enchilada approach. You can use one of the approximate approaches, that is a half-time approach, the initial slope approach, or the late time slope to estimate diffusion coefficients. And all of those ought to give you comparable values. And if they don't, then this is an internal check on the consistency of the experimental data. Now, the derivation of these analytical models has assumed that the diffusion coefficient is constant. And so what happens if that's not the case? Well, you can solve the partial differential equation numerically, assuming that the diffusion coefficient depends on concentration, and that's not a problem. But I want to show you how the results change in terms of what you would see in an experiment. And so this is again plotting fractional mass uptake as a function of t to the 1/2. And now for a case where the diffusion coefficients are changing with concentration, with local concentration inside the sample. And the model that's being used here is a linear one. That is that the diffusion coefficient starts at some value d0 and increases with a slope a that's proportional to the fractional concentration in the sample. And so when a is equal to 0, you just have the constant diffusion coefficient case, which we've been talking about. When a is equal to 2.5, indicating that the diffusion coefficient changes by a factor of 2.5 over the course of this experiment, this is what the fractional mass uptake looks like. And so, as you might imagine, if the diffusion coefficient is increasing as the concentration goes up, then you would have later in the experiment, the fractional mass uptake would go up. The effective average diffusion coefficient is higher in this case. But look at the structure of this. It's just perfectly linear and then bends over again. Well, if you make the diffusion coefficient more concentration dependent, it goes up by a factor of 4.8, a factor of 10 during the experiment. You still see the basic structure of the experiment is fractional mass uptake is linear with time and eventually bends over to asymptotically approach a value of 1. And it turns out that the use of these equations to model such data is reasonable. And the question is, what is the value of the diffusion coefficient that you would extract from such experiments, and how does it relate to the concentration dependent diffusion coefficient? This is showing another set of these data now for desorption, and again you see similar behavior, that even if the diffusion coefficient depends strongly on concentration, the fractional mass uptake kinetics are initially linear with square root of time. This is showing a different model where the diffusion coefficient increases exponentially, and is showing cases where it changes by a factor of 10 and by a factor of 25 during the course of the experiment. And you again see fractional increase in mass uptake kinetics with square root time initially bending over to towards equilibrium. And what Crank has shown is that to a very good approximation, the value of the diffusion coefficient that you deduce from the absorption experiments, that is from the slope of that line or from fitting the model that assumes D is constant, the value of the diffusion coefficient you get is within a few percent the integral value of the diffusion coefficient integrated over the range of the concentration that is experienced by the sample during that experiment. And so we can apply this methodology to estimate effective or average diffusion coefficients, even in cases where the diffusion coefficients, the underlying diffusion coefficients are changing with concentration. And we have a methodology then to relate those average diffusion coefficients back to the concentration-dependent diffusion coefficients. And you can imagine that if you did a series of experiments where you varied the concentration at which you did the step jump to, so you varied C0 and measured D bar as a function of C0, you could actually differentiate this expression and get back to D sub C, the underlying native concentration-dependent diffusion coefficient. And so this is showing the difference between the average diffusion coefficient that you would calculate from solving the transient diffusion equation rigorously versus the approximation that is shown here when the diffusion coefficient varies linearly or exponentially with concentration and where the absolute magnitude of change in the diffusion coefficient is factor of 2, factor of 10, factor of 20, and factor of 30. And the deviation between this approximate model for the relationship between those two and the actual values goes on the order of 15 to 20% at most. And I can tell you that in making measurements of diffusion coefficients in this field, it's hard to measure them that accurately. And so for all intents and purposes, this is a reasonable approximation. Now, that's the case for diffusion in a plane sheet. And we've gone over that in some detail because, one, it's an important case for membranes, for a number of controlled drug delivery devices, but also because all of the characteristics of the solution here carry over to other geometries. And so we'll also talk about fibers or cylindrical diffusion in the cylindrical systems. This is really important in things like fiber dyeing. You can imagine that if you make textile fibers and you don't want them all transparent or white, then you apply dye to them, and that dye infiltration into those fibers is a diffusion process. There are also drug delivery devices that are cylindrical, where infusion of drug into those devices or removal of drug is governed by these same results. And so the basic geometry is shown here. The basic differential equation in cylindrical coordinates looks very similar in principle to the one we saw earlier. Typically, in things like fiber dyeing or controlled drug delivery, the aspect ratio of the fibers is such that the fast direction for mass transfer is the radial direction, right? You don't have, a short, stubby fiber, but it's a long, thin cylindrical fiber. And in that case, it's only the transport in the radial direction that is limited. The boundary conditions are quite similar to the ones that we looked at for the flat plate. That is, at T less than 0, the initial concentration of penetrant is C0, and at T greater than 0, the boundary is stepped up to a new concentration, C1. And with these boundary conditions, this is the solution for the concentration profile. As in the solution of these kinds of problems in You always see Bessel functions appearing, as opposed to, for example, sines and cosines in the planar sheet case. This is this is showing the concentration profiles. Again, the characteristic value for making time dimensionless is dt now over r squared. A in crank is the radius r, which I called r throughout here. And again, you can see that by the time you get to dt over r squared equal to 1, the diffusion is over. Any mass transfer that could occur has occurred. This expression can be integrated to calculate the fractional mass gain or loss, and there are one expression is shown here. This can be expanded to get the expression shown at the bottom of the page. And again, you see a characteristic that the fractional mass uptake at some short time goes linear with the square root of time. This is characteristic of diffusion in any geometry, that at short enough times, fractional mass uptake increases linearly with the square root of time. And this is showing the plots of that of those data for the solid cylinder, which is the one we were just looking at, and also for hollow cylinders. And you don't need much of an interior part of the cylinder to be hollow before the result starts to look an awful lot like the fractional mass uptake for a plain sheet. You can imagine that if this interior hollow cylinder were almost equal to B, then this would look like just a thin, it would look like my little plain sheet wrapped over, right? And then you should expect that the fractional mass uptake kinetics would be the flat sheet kinetics. And that's what's shown here. But what's interesting is you don't need to be all that thin before you get very close to the flat sheet kinetics. So anyway, that only leaves one other possibility, right? You know, plain sheet, cylinder, spheres, and there's a number of cases where removal of solvent from polymer pellets or drying of powders, the release of drug from spherical drug delivery devices, where the kinetics of transport in spherical systems is of interest. Again, I write the general result for Fick's law in a spherical system, and these systems are often organized so that the concentration, there are no concentration gradients in the theta or phi directions, and the system, the sphere itself, is sitting in a bath where the concentration all around it is constant, and in that case, only the mass transfer in the radial direction is important. With all of the spherical systems, in terms of getting analytical solutions to the differential equations, there's a trick that is to let a new variable u equal the product of c times r. And if you do that, this differential equation transforms into this one. And this one then looks like a plain sheet equation, right? So you go back to a lot of those plain sheet solutions have analogs in spherical systems. And so for sorption or desorption experiments, the initial conditions are that at t equals 0, u is equal to r times c0. And so if c0 is constant, u will just be equal to r. If c0 is 0, then u will just be equal to 0. And at t greater than 0, u is equal to r. U is equal to 0 at r equals 0, and it's equal to r times whatever the concentration is at the exterior of the sphere times r times c1. And so the solution for the concentration profile is shown here, and again, it looks an awful lot like the solution to the plane sheet problem. That's no coincidence. If the underlying differential equation is analogous and the boundary conditions are similar, then the solutions to that differential equation are going to look quite similar. Again, those are the concentration profiles. You'll see that it is that the solutions here look very much like the solutions that we saw earlier. One of the things that you'll note is that you don't need to get to nearly as high a value of dt over r squared before the diffusion is essentially over, and this reflects a really basic phenomena that as you go from flat sheet to cylinder to sphere, you have an improvement in surface to volume ratio, and the mass transfer is always proportional to the surface area, and so the diffusion simply, all other factors being equal, is faster in a spherical system than it would be in a plane sheet or a cylindrical system. Those are like the two pearls of wisdom I can impart you with today. I can't overemphasize the importance of surface to volume ratio in chemical engineering, and that dt over characteristic dimension squared equals 1 means diffusion is over. You'll live a long and prosperous life with those two guidelines. And so this is just comparing the concentration profiles that we've seen in the sphere with those in the cylinder. And again, you see that in the sphere, you don't go to as large a value of dt over the radius squared as you do in the cylinder before the diffusion is effectively over. Here's a comparison between the sphere and the slab. And again, you see these profiles, they look similar. And that's because the underlying differential equations look similar, and the geometry does have an effect. It changes the surface to volume ratio, and that does have an effect on how fast the diffusion comes to equilibrium. But the basic phenomena look similar, independent of geometry. The concentration is converted to fractional mass gain or loss by integrating over the volume, and the concentration over the volume to calculate the mass. And again, you see the expression looks very similar to what we would have seen in a slab. This exponential, if you we can also get a term that is, or a variation of the solution in terms of error functions, and it allows an easy extraction of the front term, so that at short times the fractional mass uptake again goes as t to the 1/2. And so that's true independent of geometry. And that turns out to be, again, a good rule of thumb that initially in any system, fractional mass uptake is going to go linear in the square root of time. I'm not going to belabor it. This is, we did a hollow rod, and so here's the solution for a hollow sphere. This is important. A lot of controlled drug delivery devices will have a drug or drug solution encapsulated by a sphere that acts as a rate controlling membrane. And so then the rate of transport through that membrane can be calculated using the expressions that are shown here. Again, this is in Crank. The only thing I'll show from this is that as you go from the solid sphere case, where the mass uptake is faster than it is in the plane sheet, to something where the thickness of that spherical layer starts to get thin, you see the solid sphere result start to approach that of a plane sheet. As the thickness of this spherical layer gets thinner and thinner, it begins to look more and more like a plane sheet. And that gives another important simplification for complex systems, is that they can often be approximated by the solution as if the system were a plane sheet. If the dimension through which the mass transfer is occurring is thin relative to the overall dimension of the system. Now we're going to start to talk about controlled drug delivery, and I should say active agent delivery, because it's not only drugs that are delivered this way. So there are things like nicotine delivery patches that are used transdermally, scopolamine transdermal delivery patches that if you're prone to get seasick, you can put on a patch for that. If you have glaucoma, there's a patch for that. Birth control, there's a variety of devices that are based on controlled drug delivery. Those are some of the earliest controlled drug delivery applications. Even your plants get a little love from this space. If you get, I don't want to push a specific product, but this one was one of the first ones to market, the Osmocote. And so these are spherical, they're fertilizer encased in spherical, in little spheres. And you put out a few of these spheres, and you don't have to fertilize your houseplants for 6 months. It's what we call a modern miracle. And these they're used in agriculture, pheromone release to control insect reproduction, insecticide release. I don't know. I remember, back before electricity, when flea collars first came out. You may have dogs or cats with flea collars. Yeah, I remember the day before there weren't flea collars, and it was not as pleasant. And then suddenly you get this little plastic collar, that you strap onto the dog, and the fleas go away. And they stay away for several weeks or a month or so, and then you put another one on. That's a controlled delivery device based on polymer impregnated with things that fleas don't like. This one is less less in vogue today, but one of a real problem in shipping is that marine organisms attach to the walls of boats, and then they can slow them down as the ships sail from harbor to harbor. It also is a problem in transporting marine organisms from one ecosystem tens of thousands of miles into another ecosystem and releasing them in environments where they're not supposed to be. There's been cross-contamination of ecosystems with non-native species due to shipping. And so today, large ocean-going vessels are typically equipped with coatings that slowly release a biocide that leaves a bad taste in the mouths of mussels and barnacles. It's less and less favored to use heavy metals for that purpose, but you get the picture. So one of the things I'd like to bring to your attention is this book, Controlled Release of Biologically Active Agents by Richard Baker. It's written some time ago, but it was written after the first wave of controlled release devices had come onto the market. So this idea had been around for many years, and there have been people trying to commercialize it. And starting in the late 70s and early 80s, controlled release devices started to appear on the market. And Richard Baker was a key practitioner in this area in industry, and also turned out to be a very good writer. And so he wrote a book that to me is the best in the field at describing the technological areas in a broad sense where these ideas apply, and also relating it back to the fundamental science, back to Fick's law, and how you use that to describe and predict the performance of these devices. Now, Richard Baker was a seminar speaker here in a symposium we had for Don Paul last October. He now runs a gas separation membrane company in Silicon Valley. And to have heard his presentation then, you would not know that he had been deeply involved in this field and had written a textbook in it. But what it signifies is that there is a basic set of science that underpins all of these applications. And if you're strong in that basic science, you can apply those skills to many different problems. And one of the things that you should be trying to do in your graduate studies is build your basic science and engineering skills. Because one thing's for sure, whatever problem you are working on today for your PhD will not be the problems you work on 5 years, 10 years, 15, 20 years from now. And so what skill set do you need that is going to be durable and is going to stand up over time to allow you to be competitive, not just today, but 20, 30, 40 years from today? And I would assert that having a strong command of underlying chemical engineering principles, things like mass transfer, heat transfer, reaction kinetics, those apply across many different fields. Being able, Christina, to make things, right? You can make things today for one application, you're in position to make things for other applications that we haven't even thought about. So synthetic skills are a valuable basic tool to have at your disposal. And as you carry out your graduate studies, be mindful not only of working on the specific problem that you're doing, but also how do you build your base skill sets, so that in the future you could be, the analog, the person who worked a long time in controlled drug delivery, wrote a textbook on it, and then went and founded an entirely new company working in different technology, but with the same underpinning science, and has been successful at that. Okay, so we'll start a little bit with the commercial. So this is there's a variety of these compounds on the market, but this is the controlled release fertilizer that I showed. That was developed, close to probably more than 20 years ago now. There's a lot of excitement when this first came out. This is scopolamine, motion sickness drug. You can take that orally, and it doesn't last as long, or you can get a patch that slowly releases scopolamine, in this case over a period of 72 hours. Put it on the carotid artery, so it's because that's near the surface where there's high levels of blood flow and where the medicine can rapidly get into blood circulation. This is a cross-section of that scopolamine release patch. There is it has like a aluminized seal on it that you peel off. There's a contact adhesive, a rate controlling membrane, drug reservoir, and then it has an impermeable backing, which is this aluminized polyester film. The scopolamine is on this side of the rate controlling membrane, so that you get fast initial release, and then there's a reservoir of it on the back side. And this microporous polypropylene film then gates the release of scopolamine out of the device, then across the skin and into the bloodstream. So you can see it's a simple device the way it's set up. There are contact lenses that are drug releasing contact lenses, and this one releases pilocarpine, which is a glaucoma treatment drug, and you can see how that is set up between what we would call the contact lenses, or rate controlling membranes, and then there's a reservoir. They sandwich a reservoir of the pilocarpine, and this is showing its release rate over time. And the key here is that the alternative way to use this glaucoma treatment drug would be to instill drops of pilocarpine into your eye, and then you get a very short burst of pilocarpine, and within a matter of minutes to an hour, it's gone. With the contact lens, you can get therapeutically effective amounts over the course of an entire day without having to constantly put these drops in your eye. This is BioLure. It is a controlled release system for pheromones. Who knows what pheromones are? Anyone? Yeah, so, okay, good.
Oh, it's the kind of hormones that like animals use and secrete to attract the mate.
Yeah, and so this is how insects would find one another, to mate. For example, things that are eating your crops. And so now what happens when you put a bunch of these boys out into the field that are releasing the pheromones all over the place? It can
You
get,
guys to kind of track them to a specific point where you want, like, where you want.
well, it gets very confusing, right? Because here's the pheromones, but where's the mate? And so this is done to, I guess the polite word is disrupt, stop destroying insect communication and reproduction. These are just little devices that are now made out of compounds that will biodegrade and then just distributed around fields. So the pheromones are in a sponge-like structure, and then with a rate controlling membrane over top of it. So this is showing release rates of different formulations of this BioLure to control cabbage loopers, and they can be formulated to release different amounts of the pheromone, and can release them certainly at slow rates of release, can release them over time periods of a couple months. And so if you imagine if you're farming, you apply insecticide, for example, or fertilizer, whatnot. And so you apply it today, it's effective. Tonight it rains, tomorrow it's gone, okay? Or something like that. If you could apply these controlled release systems, you don't have to come back every week or 2 weeks. You can apply it once over the entire growing season. It markedly cuts down the labor associated with farming, and then you're getting continuous protection. And so it's better than just the spike delivery that you get by manually applying chemicals and fertilizers from time to time. It also cuts down on the overuse of those types of chemicals, because if you have to apply them manually each time, the tendency is you over-apply them to get a somewhat longer period of efficacy. And so there's a period of time where you got way too much chemical out there to be effective, and that can have other detrimental impacts on the environment. And so one benefit of these controlled release systems is that they can help even out the use of drugs, insecticides, fertilizers, you name it, at rates that are therapeutically useful but not too high. This is an example of a nicotine control release patch, and it has similarly an adhesive, a rate controlling membrane, a drug reservoir, and then impermeable backing on it. These you can now buy over the counter in drugstores, and I think probably even grocery stores as well. I always thought this was, well, anyway. And then there's been another extension of that concept. Yeah, anyway. So the idea behind the controlled release devices is that they allow greater efficacy than traditional mechanisms of release. So historically, to get a therapeutic level of a drug into your system for a significant period of time, by either pills or injection, it was often the case that you would you inject or dose with more of the drug than you need, and then in order to have some efficacy later. So there's two levels of of use, for example, of a drug. One is there's a level below which the drug is ineffective. So, you know, if you've got like a splitting headache and I offer you 100th of a Tylenol, how much is that gonna help? Probably not much. So there is a level below which the medication is ineffective. There's also a level above which it's toxic. And so, you got a splitting headache and I give you 20 Tylenol, right? And so what's happening is that typically, you get an injection or you take medication in order to maintain an amount that's above the ineffective level over a useful period of time. You're often taking a lot more initially than you need, and gradually that's metabolized and the rate comes down, and then you have to take it again, and you go through this cycle again. The idea behind controlled release technology is to release an amount of drug over long periods of time in this therapeutically effective window without ever going through these cycles where you're above the toxic limit or below the ineffective limit. And so that's the objective of this. Now, most of these devices are based on systems where polymers are the rate controlling devices. There are 3 release profiles that one can obtain based on the laws of diffusion. One is so-called first order kinetics, where the release rate just starts at some initial value and falls off with decaying exponential. We'll show you how these come about. It shouldn't be a surprise that one can get release rates that go according to square root of time kinetics, right? We just said square root of time, square root of time, square root of time. And so it shouldn't be surprising that then the rate of release, which would be the fractional mass loss from this device, would go with the square root of time. And then there's a case that has been of great interest in the field, and that is one can organize devices so they operate at 0 order kinetics, that is where the release rate is independent of time. And these devices often have a short transient period at the beginning of operation of the device, and like any of these devices, when they finally run out of medicine, the release rate ultimately drops to 0 at some point. And so what we're going to talk about over the next lecture or so is how to set up devices so that you get these release profiles and you know when to expect which type of release profile, and then to give you practical examples of where those are used. There are basically 4 types of controlled release systems that are in use practically, and there are so-called reservoir systems, and so this is where you have a reservoir of drug behind a rate controlling membrane, and that membrane then governs the rate at which the active ingredient is removed from the membrane into the environment. There are matrix systems in which the active ingredient is just dispersed or dissolved in a polymer matrix, and it's released from that matrix by diffusion of the active ingredient through the polymer matrix. So this, you can imagine, might give square root of time release kinetics, because this would be like the absorption-desorption curves we were looking at for propane into that polymer, or sodium chloride coming out of the polymer. There are swelling control systems, and these are ones in which you would put an active agent into a polymer matrix, and where inherently that active agent will not come out of the polymer matrix until it comes in contact with an external agent, and that could be water, it could be pH, sensitive, so you set these devices to swell, and when they swell by imbibing water or other bodily fluids, then the drug is released from the swollen polymer, and you can set the triggers so that they're pH sensitive, so that they might release in your stomach, in your upper intestine, lower intestine, and so you can control where the drug would be released. There are osmotic systems where these are not all drugs or active ingredients that you might be interested in releasing are highly water soluble or are ready to diffuse out into the bloodstream or in the surrounding tissue with absolutely no help at all. And for those types of devices, you can imagine almost like a syringe with the active agent and a end on it with a tip. And behind that syringe is another chamber that would have, for example, salt or some other osmotic agent. And this device comes into contact with water or other bodily fluids. The salt or this osmotic agent will imbibe water and it will swell. And as it swells, it pushes the plunger on this drug reservoir and the drug comes out the end of it. And so those would be examples of osmotic systems that are used to release drugs that wouldn't be easily releasable by these other mechanisms. The basic analysis of these problems is based around Fick's law, and this is what we've been studying this semester. And the reason we apply this is because it's so useful in predicting, not only from a fundamental point of view, but a practical point of view, the operation of these kinds of devices. It's often very typical that if the membrane is the rate controlling step in controlled release, well, the flux would be proportional to the concentration gradient of the active agent in the membrane. That's often inconvenient to measure. It's often much more convenient to measure the concentration of the active agent in the environment surrounding the membrane, that is in the reservoir or in the fluid or system that's outside the membrane. And so very typically the concentrations inside the membrane are replaced by the concentration in the external solution by using a partition coefficient. So this partition coefficient or solubility coefficient gives the relationship between the concentration outside and the concentration inside the membrane. And if this partition coefficient doesn't depend much on the active agent concentration, you can recast Fick's law in the form that's shown here. Now, what do you think D times K would be? Oh, look at that, it shows up again, right? And so, P is D times K, or in the case of gas transport, P is D times S, drops ubiquitously and naturally out of the governing equations for these types of systems. And so formally one can integrate that expression and express it in terms of the permeability coefficient and the average diffusion coefficient as indicated by earlier by Fick is given here. These are going to be the start of actually getting into some of the discussion of controlled delivery devices. So I think I'm going to stop the lecture here before we go any further.